Hello students, and welcome to our lesson on solving quadratic equations. First things first, what is a quadratic equation? So a polynomial is considered quadratic when it has a degree of 2. Now the degree, if this is your first time hearing this word, okay, the degree is the highest exponent. So when we look at an equation, if the highest exponent on any variable is a 2, then we would say the degree is 2. So now the degree is important because it tells us the number of possible solutions to the equation. So in general, because we're going to be dealing with quadratics here, we will always expect there to be two solutions. But those two solutions will not always look the same. And in some cases, those two solutions are the exact same thing. So in that case, we would say that there's only actually one unique solution. But it's not that there's really only one solution, it's just that two of them are the same, so we don't write them separately. So that being said, let's see a couple examples here of what solutions might look like. All we're going to be doing in these next couple problems is square rooting both sides and see what x looks like when it's by itself. So for the first one, x squared equals 4. If we square root both sides, we would say that x is equal to plus or minus the square root of 4. Okay, because when we take that square root on both sides, we need to put a plus minus in front of the radical. Now, the square root of 4 is 2, so we can say x here is equal to plus or minus 2. Because we get two real numbers here, we get positive 2 and negative 2, we would say that there is two real solutions. Where by real, we mean that they are real numbers. There's no I involved, and these numbers actually exist in the real number system. Not only would we say that they're real, though, we would also say that they are rational. So we have two real solutions, and they are both rational. And by rational, what we mean is that they simplify nicely to be an integer divided by an integer. In this case, 2 over 1 and negative 2 over 1. For the second example, when we square root both sides, we're going to get x equals plus or minus the square root of 5, where the square root of 5 does not simplify, and so we would say that there's still two real solutions. Okay, so two real solutions still. Square root of 5 and negative square root of 5 are both real, but they are irrational. Okay, because the square root of 5 does not simplify to be an integer over an integer, because we can't take the square root of 5. It's not a perfect square. Sorry, we can take it, but it would not simplify nicely. It is not a rational number. We say that we have two real solutions, but they are irrational. Now the next one, x squared equals 0. We square root both sides. We get x equals plus or minus the square root of 0. But square root of 0 is just 0, and positive and negative 0 are the same thing. So we just get x equals 0. In this case, we would say that there is one real solution. And in this case, it's actually that we have two solutions that are the same thing. Positive 0 and negative 0 just give us 0 twice. When we learn more about quadratics, which for most of you will be in a separate class than this, but when you learn more about quadratics, you'll learn what a double root is and how that affects the shape of a quadratic when graphing it. But essentially what happens here is we get the same answer twice. And so although we say there's only one real solution, really it's two real solutions that just are not distinct. They are the same solution. All right, and then the last one, if we square root both sides of x squared equals negative 4, we get x equals plus or minus the square root of negative 4. If this is your first time seeing the square root of a negative number, all you do is pull that negative sign out as an I. Okay, the letter I gives us the square root of negative 1. And the square root of 4 is 2, so we have 2i here. So plus or minus 2i, where these are what we call imaginary numbers. And so we would go through all the same steps here, get to the same answer, but at the end we would just claim that this is two imaginary answers. And I'm actually going to switch away from the word imaginary. I'm going to use the word complex here because that is the more technically correct answer. So two complex solutions. And what complex means is it's a combination of real and imaginary. In this case, plus or minus 2i, those are purely imaginary values, but we might have like 1 plus 2i, which would be a complex answer. And all imaginary and all real solutions are also complex. So complex is a little general here, but we get two complex solutions, which could also be referred to in this case as imaginary solutions. So overall, we would say that quadratic equations will have either two real solutions, which could be rational or irrational, one real solution, which will always be rational if there's only one real one, or two complex slash imaginary solutions. And notice there they used complex slash imaginary because it really could be either one. They could be fully complex or fully imaginary. Sorry, fully imaginary or complex in general. So now moving on, when we want to solve a quadratic equation using the square root method, which we will use for these first four examples here, what we're going to do is get the squared term isolated. So we want to make sure that the squared term is all by itself on one side of the equation. So notice in the previous examples, we had x squared all alone in each of these. That way I could easily square root both sides. Okay, so we're going to get that squared term isolated. We're going to get rid of the square by taking the square root of both sides of the equation. And you must remember to put the plus minus symbol in front of the number you took the square root of. So up here at the top, when I was doing that, even though I was only writing x and then the square root on the other side, what I'm technically doing is doing the square root of x squared equals the square root of 4. And when we do that step, we're taking the square root of both sides, and the square root of x squared is actually the absolute value of x, which is what causes us to put this plus minus here. So we can kind of skip those two middle steps by just saying take the square root of both sides, where on the left it just becomes x, so the squared goes away. And on the right side, we put the plus minus in front of the square root of the number. So we're actually skipping two steps by doing that. All right, and if necessary, which in some of these it will be, you may still need to get x isolated in order to have your final answer. All right, let's go ahead and try. You may be tempted to put these equations into standard form and use factoring, but on this first four examples, we want to avoid that. Okay, we're going to see what it looks like to solve by factoring on the next page. So here, what we want to do is isolate the square term. So we have 2x squared minus 1 equals 17. If I add 1 to both sides, I get 2x squared equals 18. Then if I divide both sides by 2, x squared is equal to 9. And now I've isolated the square term. So these first two steps here, I isolated the square term. Now, once you isolate the square term, then you square root both sides, where the term that is squared, when you square root it, you just get whatever was squared. So when I square root x squared, I'm just going to get x. And on the right side, when I square root 9, I'm going to put a plus or minus in front of that square root. So notice the left side, all I did was get rid of the 2 as the exponent. But on the right side, I wrote plus or minus and then the square root of the number. So what I just did right there was square root both sides. And then now we're going to simplify. So the square root of 9 is 3. So we get plus or minus 3. And then we can just write our answers separately. We could say that x equals 3 or x equals negative 3. So we get two answers at the end. All right, and those last two steps, just to be ultra clear here, from the square root of 9 down to my answer, this was just simplifying. So simplify. So we're going to isolate the square term, we're going to square root both sides, and then we're going to simplify. All right, number 2, I'm going to start just by like solving a normal equation the way we would a linear equation. We're just going to try to get this square term by itself. So I'm going to subtract 2 from both sides to get x over 5 equals negative 5. Then I'll get rid of that denominator by multiplying both sides by 5. So x squared equals negative 25. Now I'm going to square root both sides. So on the left, I'll just write the x. I'm going to get rid of that exponent. And on the right, I'll write plus or minus the square root of negative 25. Now I'm going to simplify this. So the square root of negative 25 gives me 5i because it was negative. And now I have plus or minus 5i, so I'll just write it as two separate answers. X equals 5i or x equals negative 5i. All right, those were two of the simpler cases. Now in problems 3 and 4, we're going to have an extra step or two at the end where we have to isolate x after we've simplified both sides. So in number 3, I have 3 times x minus 5 squared equals negative 27. First, I'm going to divide by that 3. So I'll get x minus 5, the whole thing squared, is equal to negative 9 when I divide by 3. Then I will square root both sides because now I have that square isolated. So when I square root both sides, I get just the x minus 5 on the left and plus or minus the square root of negative 9 on the right. So very simple. When we square root both sides here, we don't even need to write the symbol on both sides because on the left, all that happens is the square goes away. So I still have x minus 5 like before, just no more exponent on top of it. But on the right side, I need the plus minus and that square root. All right, now we're going to simplify a little bit. So we have x minus 5 is equal to plus or minus negative 9 when we square root it gives us 3i. Now I'll add 5 to both sides to get x equals 5 plus or minus 3i, where I can't combine the 5 and the 3i because they are not like terms. So I added the 5 to both sides, but then I just leave them separate, 5 plus or minus the 3i, separate pieces. And now my final answer is either x equals 5 plus 3i or x equals 5 minus 3i, because that plus minus can always be split up into two problems. All right, number 4, same idea. We're going to start by, instead of dividing both sides, in this case we have to add 2 to both sides. So x plus 1 squared is equal to 24. I now have the square isolated, so I square root both sides. On the left, the exponent just goes away. On the right side, I'm going to get plus or minus the square root of 24. Now, 24, if this is your first time simplifying a radical, 24 breaks down to be 4 times 6. 4 is 2 times 2, and 6 is 2 times 3. So all in all, we could say that 24 is equal to 2 cubed times 3. So now what I'm looking for when I simplify a radical is groups of 2. So if I want groups of 2, what I can do is just divide the exponents on that prime factorization by 2, and then leave the remainder behind and take the quotient out. So what I mean by that is right here I have 2 cubed in the bottom right. Okay, the exponent is a 3. So if I take that exponent of 3, what I'm going to do is divide it by 2 because the index of my radical is 2. So over here on this square root 24, we have square root is really, it's the opposite of the squaring. So it's a 2 as our index. Okay, so 2 cubed, if I divide the exponent by 2, I get 1 with a remainder of 1. So 2 cubed is actually equal to 2 squared times 2 to the power 1. Because notice 2 plus 1 would give me 3 there. And when I divide by 2, this 2 squared becomes 1, 2 on the outside. All right, so now all that being said, if we go back a couple steps, because that was the real technical way to explain, in simplicity, all we're doing is looking for groups of 2. So I have a 2, a 2, a 2, and a 3. These two 2's right here will become 1, 2 on the outside. And because the 2 and the 3 don't have any pairs, they stay on the inside. So when I rewrite this, I'm going to get plus or minus 2 square root 2 times 3. Where notice these 2, because they're a group of 2, they become 1, 2 on the outside. And because this other 2 and 3 didn't have anything to group with, they stay on the inside. So we now have that x plus 1 is equal to plus or minus 2 square root 2 times 3. If I multiply the 2 and the 3 back together, I have 2 square root 6. So the square root of 24 is just 2 square root 6. Now if I subtract 1 from both sides, we're going to get our final answer, which is x is equal to negative 1 plus or minus 2 square root 6. So now I can just split it into two answers. Either x is negative 1 plus 2 square root 6, or x is negative 1 minus 2 square root 6. All right, so now I have one for you to try. So we have x minus 3 squared plus 1 is equal to 17. Give it a chance. All right, hopefully you paused and tried it. So if I subtract 1 from both sides here, I'm going to get my square term isolated, and I'll have 16 on the other side. By square rooting both sides, we get x minus 3 is equal to plus or minus the square root of 16. So that means that x minus 3 is equal to plus or minus 4. When I add 3 to both sides, I get x equals 3 plus or minus 4. And now when I split this into two problems, 3 plus 4 is going to give me 7, and 3 minus 4 is going to give me negative 1. So I end up with 7 or negative 1 as my two solutions for x. And that was the square root method. So now we're going to go a different direction. We're going to solve by factoring. So now solving by factoring, in my opinion, is more fun because I just enjoy the factoring process. But first things first, we have some steps. So to solve by factoring, we're going to get the equation in standard form, which as you recall is ax plus ax squared plus bx plus c. We're going to factor it completely. And the solutions are going to be the values of x that make each factor equal to 0. So we're going to use what's called the zero product property to set each factor individually equal to 0. And sorry, I did forget one thing here. Standard form is ax squared plus bx plus c equals 0. So the key is that we're going to be getting 0 on one side and standard form on the other side. All right, so now one little note on setting all factors equal to 0. We're going to use what is called the zero product property, which states that if you have a times b equals 0, either a equals 0 or b equals 0. So once we get things factored to where we have the product of two things is equal to 0, either the first thing is 0 or the second thing is 0. Okay, and that zero product property is what is going to allow us to actually solve these questions. All right, so now we got to do some factoring. In problem 5, we already have standard form, so we can go straight to factoring. Recall from factoring by splitting the middle, the AC method, we multiply the A times the C, which is 1 times 12 gives us 12. That goes in the top left. The B term is 13. So now I need two numbers that multiply to give me 12 but add to give me 13. And those two numbers are going to be 12 and 1 because 12 plus 1 is 12, or sorry, 12 times 1 is 12 and 12 plus 1 is 13. So we add up to 13 over there, and 12 and 1 are what I will use to split the middle. Now you may have learned that when the A value is 1, you can actually skip the splitting the middle process, but because that wasn't explicitly covered for us, we're not going to be doing that. We're going to actually do the splitting the middle steps, but this will end up being x plus 12 times x plus 1 if you are comfortable jumping to that. But doing the split in the middle process, we have 12x plus 1x is what we split our middle into. X squared in front and 12 in back, and this is all equal to 0 still. On the left, we split it into two groups. The first group, I can pull out an x to leave behind x plus 12. The second group is already x plus 12, so I just pull out a 1, still equal to 0. We pull the x plus 12 to the front, and we leave behind the x plus 1. So now we have the product of two things is equal to 0, where over here where I wrote a times b equals 0, a is x plus 12, and b is x plus 1. So what the zero product property allows us to do is split this into two questions. Either x plus 12 equals 0 or x plus 1 equals 0. Okay, that is using the zero product property I wrote in pink. So let me actually write this in pink, that way it's the same. There we go. So now using the fact that either x plus 12 equals 0 or x plus 1 equals 0, the left one we can solve by just subtracting 12 to get x equals negative 12. And the right one, we subtract 1 to get x equals negative 1. And then we have two answers. Either x is negative 12 or x is negative 1. And we expected two solutions because remember the degree is 2. And so we expect two answers to come out of this. All right, for the next one, we do not have standard form yet. 5x squared minus 8x equals 4. I need to move that 4 to the other side by subtracting it to get this into standard form first. Now that I have standard form, I can go ahead and split the middle. So I'm going to make a t-chart to do the AC method. 5 times negative 4 is negative 20. The b term is negative 8. I need two numbers that multiply to give me negative 20, but add to give me negative 8. So I might try negative 5 times 4, but those add together to be negative 1. So those are too close together. So then I might try negative 10 times 2, and those do in fact add up to be negative 8. So I found my two numbers. I take the negative 10 and the 2, and I split the b term into negative 10x plus 2x. The first term stays in front, and the minus 4 stays in the back, all equal to 0. I can factor by grouping by splitting the problem in half. From the first group, I can pull out a 5x to leave behind x minus 2. From the second group, I can pull out a 2 to also leave behind x minus 2. Then that x minus 2 comes to the front. I leave behind 5x plus 2, all still equal to 0. And so now again, we use the zero product property to split this into either x minus 2 equals 0 or 5x plus 2 equals 0. So two separate problems. We solve them individually now. If x minus 2 is 0, that means x equals 2. That's one of our answers. And if 5x plus 2 is 0, that means 5x equals negative 2. So then we divide by 5 to get x equals negative 2/5, and that is our other answer. So again, we get two solutions. This one required a little bit more solving at the end for that 5x plus 2 component, but really it's the exact same process for both problems. Factor, and then use the zero product property. All right, number 7. We already have standard form. Oh, no, we don't. Look at that x over there on the right side. So we don't have standard form, which means we are going to have to convert this into standard form. So in order to do that, I subtract x from both sides to get negative 4x in the middle there. Now, originally, it looked like I was going to be able to pull a 3 out, but when I moved that x over, now there is no GCF I can pull out. So instead, we'll just go straight to the AC method. 15 times negative 3 is negative 45, and our b term is negative 4. The two numbers that are going to work are negative 9 times positive 5. Okay, and those add together to give us that negative 4 that we want. And so this means that we can go ahead and split the middle, negative 4x, into negative 9x plus 5x. So I split the middle there. 15x squared in front, negative 3 and equals 0 in the back. Split the problem in half using a line. The first set, I can pull out a 3x to leave behind 5x minus 3. The second set is 5x minus 3, so I'm just going to pull a 1 out. I can move that 5x minus 3 to the front, and that leaves behind 3x plus 1. I now set each of these individually equal to 0 because the zero product property says that if we have the product of two things equal 0, either the first thing is 0 or the second thing is 0. Now solving individually, if 5x minus 3 is 0, that means 5x is equal to 3, which means x equals to 3 over 5. Or if 3x plus 1 is 0, that would mean 3x equals negative 1, so x equals negative 1/3. Okay, so I get two answers just like in the other problems, but in this case, both factors had two extra steps at the end. All right, one more. It's a you try. Please pause the video and give it a chance. Make sure you put it into standard form before you get going. All right, hopefully you did what I told you to and paused because this is your last opportunity to get a chance in this video. So hopefully you took it. So 10x squared in front, 11x in the middle, negative 6 in the back. We now have standard form. If we use the AC method, 10 times negative 6 is negative 60, and the b term is 11. The two numbers that are going to work here, let's see, let's try negative 15 times 4. Oh, those add up to be negative 11, so that's not quite right. If I try positive 15 and negative 4 though, 15 plus negative 4 does equal 11. So those are going to be our two numbers. So I can go ahead and split my middle term here into, instead of 11x, 15x minus 4x. I'm going to put 10x squared in front. I'm going to put negative 6 equals 0 in back. Draw a line down the middle. The first group, I can pull a 5x out to leave behind, in this case, 2x plus 3. In the second group, I have a negative 4 in front, So I'm automatically going to pull out a negative, and then a 2 is the GCF of 4 and 6. So I pull out that negative 2. That leaves behind, again, a 2x plus 3. We move that 2x plus 3 to the front, leaving behind 5x minus 2. And now that we have it factored and the product of two things is equal to 0, the zero product property allows me to split it into either 2x plus 3 equals 0 or 5x minus 2 equals 0. Solving those individually, we could say that 2x equals negative 3, which means x equals negative 3 over 2. Or if 5x minus 2 is 0, that means 5x equals 2. So x equals 2 over 5. And that is how you solve quadratic equations. In this lesson, we did not talk about the quadratic formula, and so we did not learn about the discriminant yet. But if you are moving farther along and you are going to learn about graphing quadratics and really all sorts of other characteristics that graphs and polynomials in general have, then the quadratic formula will become relevant pretty soon here. But for us, that is the end. Thank you for joining me, and I will see you when I see you.